Hello. In this lecture, I'm going to discuss how to calculate pH of a mixture containing two weak acids, very particularly monobasic weak acids. Okay, yeah. So pH of a mixture, pH of a mixture containing pH of a mixture of two weak acids. Okay, here the two weak acids are monobasic acids. Right. Yes, how to proceed? Let me take two monobasic weak acids, HA and HB. Now both are weak acids. Okay. Let the concentration of the weak acid HA is C1 and the concentration of the weak acid HB is C2. Okay, in the solution. That is before undergoing dissociation. Right. Now, since both are weak acid, they undergo partial ionization. So HA will undergo partial ionization and gives H plus and A minus ion. Okay. If I take 1 mole initially, right? If say for example, if x1 mole react, I'll get x1 mole of if x1 mole dissociate, I'll get x1 mole of H plus and x1 mole of A minus. Since the initial concentration is C1, okay, the concentration at equilibrium is 1 minus x1 into C1 for acid, and concentration of H plus at equilibrium is x1 into C1. This is also x1 into C1. Right. Then the weak acid HB also undergo partial ionization and gives H plus and B minus. Okay. If the initial concentration, if we have 1 mole initially, and from 1 mole let us assume x2 mole dissociate, you will get x2 mole of this and x2 mole of this. And since the initial concentration, okay, there is a concentration before dissociation, right, we assume it as C2. So multiply this by C2, this by C2 and this by C2, will get equilibrium concentrations. Since both these acids are present in the same mixture, okay, the total concentration of H plus, right, total concentration of H plus is the sum of these two, that is x1 into C1 plus x2 into C2. C1 value, C2 value we know, but we don't know what is the value of x1 and x2. Okay, so how to proceed this? Right, now we can write the equilibrium constant for this acid. Let me write the equilibrium constant as Ka1. Ka1 equal to equilibrium concentration of H plus ion. Now the equilibrium concentration of H plus ion is this, that is x1 into C1 plus x2 into C2 into then the concentration of A minus ion, which is x1 into C1, divided by 1 minus x1 into C1. Okay, we can cancel this C1 and this C1, so we get Ka1 equal to x1 into C1 plus x2 into C2 into x1 whole divided by 1 minus x1. Right. Similarly, for the other weak acid HB, we can write the equilibrium constant as Kb1. Kb1 equal to equilibrium concentration of H plus, which is nothing but the total value x1 C1 plus x2 C2 into equilibrium concentration of B minus, which is x2 into C2 whole divided by 1 minus x2 into C2. This is the formula we used to calculate Kb1. Kb1 C2 you can cancel, so I can write this as x1 C1 plus x2 C2 into x2 whole divided by 1 minus x2. Right. So this is dissociation constant for this weak acid HA, and this is dissociation Kb1 is the dissociation constant for the weak acid HB. Now what I am going to do, I'll multiply both sides of this equation by C1 and both sides of this equation by C2. But before doing that, let me make some assumption here. Yeah, I'll make some simple assumptions here. What is that? Suppose if the value of x1 is extremely small, right? Yeah, here also the common ion will effect will operate. Common ion effect will operate. Therefore, the degree of dissociation is suppressed. So, x1 value and x2 value both are very, very small. Suppose if x1 is less than 0.05, if x1 is less than 0.05, then this 1 minus x1, right, becomes approximately equal to 1. You can neglect x1. Similarly, if x2 is less than 0.05, then we can neglect x2 here. So 1 minus x2 is approximately equal to 1. So I am going to make this as 1 and this as 1. Therefore, I'll get Ka1 equal to x1 c1 plus x2 c2 into x1. Similarly, Kb1 equal to x1 c1 plus x2 c2 into x2. Right. Now what I'm going to do, I'll multiply both sides by c1. So if I multiply both sides by c1, I'll get Ka1 into, let me write c1 here, c1 x1 c1 plus x2 c2 into x1 into c1. I multiplied both sides by c1. Okay. Now similarly, if I multiply both sides of this equation by c2, I'll get c2 into Kb1. I'm sorry, this is not Kb1, Ka2. I'm very sorry. It's Ka2. Both are acid. No, I'm sorry, I made a mistake. Let me make this correction here. This is Ka2. Right? A represent acid. So this is Ka2. This is also Ka2. Okay. So dissociation constant of the weak acid Ha is represented as Ka1. Dissociation constant of the weak acid Hb is represented as Ka2. So I multiplied the equation both sides by C2. I'll get x1 c1 plus x2 c2 into x2 into c2. Now we got two equations. I'm going to add the two equations. So if I add, I'll get c1 into Ka1 plus c2 into Ka2. I'm adding the left hand sides. In right hand side, see here we have x1 c1 plus x2 c2. Here also we have x1 plus c1 and x2 c2. So I can take x1 c1 plus x2 c2 as common. So x1 c1 plus x2 c2, I am going to take this as common. If I take this as common, here we left with x1 c1, here we left with x2 c2. Okay, and see again these two are same. So if I multiply it, I'll get x1 c1 plus x2 c2 the whole square. Right? And what is this value? Take square root both sides. So therefore we can write x1 c1 plus x2 c2 is equal to square root of, okay, c1 into Ka1 plus c2 into Ka2. This will give me, okay, this is nothing but H plus ion concentration. See here, total H plus ion concentration at equilibrium is nothing but x1 c1 plus x2 c2. So we can find this value by using this formula, right? So this is nothing but the H plus ion concentration at equilibrium, right? So is equal to c1 into Ka1 plus c2 into Ka2 whole power of. We can write like this, right? From this, by knowing the value of H plus, you can calculate pH. How? We know the formula, pH equal to, let me write here. We know that pH equal to negative common logarithm of concentration of H plus ion. So minus log base 10. H plus ion concentration is this, C1 into Ka1 plus C2 into Ka2 whole power half. Bring the half in front. So minus 1 by 2 into log base 10 C1 into Ka1 plus C2 into Ka2. This will give me the pH for solution containing two weak acids under the assumption that x1 is less than 0.05 and x2 also 0.05, less than 0.05. If definitely due to common ion effect the values will be very low. If x1 x2 both are lesser than 0.05, you can use this expression to calculate pH of the mixture containing two weak acids. Okay, what are the quantities? This quantity Ka1, it is a constant, is well known value, and this is a constant, is also well known value at a given temperature. So these values are known already. If you know the concentrations of the two weak acids, yes, you can calculate pH directly. Okay, if you vary the concentrations of the two weak acids, right, then pH will also change. So at a given concentration of weak acid 1 and weak acid 2, okay, and for a given value of K, for the value of Ka1, Ka2 at a particular temperature, you can calculate the pH of a mixture containing two weak acids. Okay, so remember this formula. It's a very useful formula to calculate pH of a mixture containing two weak acids. Right? Yeah, we'll do problems. Okay, we'll do numerical problems as we go along in this series of lectures. Okay, I stop here. We'll continue this in the next class. Thank you.